MacMaths, let's do some maths today. Hi guys, I'm out filming on location again. I'm in my office, so I apologise if the phone goes. We're looking at lesson 2. We've done geometric sequences, we've done the sum of a sequence. That is one version of the formula, but we can have R and 1 the other way around, can't we? But I'm going to use that one today. And we're looking at a little quirk of this formula is what happens in some cases. It doesn't get when the sequence doesn't keep getting bigger and bigger and bigger. It actually gets smaller and smaller and smaller. The terms get smaller and smaller and smaller. Sorry, and we get a sum to infinity. Okay. So let's just explain that. The example I used, because I did have a lesson the other day with some of the students in it, and the example I used was, if you take the length of my classroom from there to there, and I wanted to walk from this side to this side, I'm walking a finite distance, okay? And let's just say that I've got a really massive classroom. Actually, my classroom was quite big, wasn't it? It wasn't 32 metres, but let's pretend it was 32 metres. So if I walked from that wall to that wall, I would walk 32 metres, okay? Now let's just suppose I started here and I walked halfway. And when I walked halfway, okay, I just paused momentarily, okay? And then I've walked 16 metres, haven't I then? And then if I pause momentarily and then I assess how far is left to walk, and then I set off again but walk half the distance to the wall, I would end up here and I'd walk another 8 metres. And then if I did it again and walked halfway to the wall and stopped, I'd walk to that point, and then I'd walk to that point. And you can see what's happening here, or I hope you can. I'll walk another 4, and then I'll walk another 2 metres, and then I'll walk another 1 metre. Because every time I pause and look at the distance and walk halfway, you know, and then stop, if I keep doing that, I'm never actually going to reach the edge of the wall, am I? Because I'm always going to be a distance away, even if that's a tiny amount, a millimetre, and I'm not going to walk up to the wall. I'm only going to walk half a millimetre at that point. And then if I'm half a millimetre away, I'm only going to walk another quarter of a millimetre, so I'm never actually going to get there. But you can see that if I did that an infinite number of times, it would be sensible to say that I reached the edge of that wall, which is, you know, 32 metres. And actually that describes a geometric sequence, that if I started with a first term a of 16 and my common ratio each time was a half, in other words I walk half the distance, so I'm timesing it by a half, the common ratio, to get the next term. My next term would be 8, my next term would be 4, my next term would be 2, then 1. You can see that all of these terms would add up to not bigger than 32, okay? So we call this a situation where we get a sum to infinity. That is, if we have an infinite number of terms, it reaches a limit, okay? Mathematicians call that a convergent sequence. And if you converge, it means that you home in on, you meet, okay? You meet a point where it doesn't get any bigger, it stops. So this is called a convergent series. The opposite of that is divergent, when it's getting bigger and bigger. If we times it by 2, we get 32, then 64, then 128. It's getting big and big and big, and as you go to infinity, it gets infinitely large. Okay, that's divergent, when it's getting bigger and bigger and bigger and expanding like the universe is at the moment. Okay, but here, this is convergent. It converges in as we keep adding terms, smaller and smaller amounts. Increasingly, it converges on 32. Okay, and that happens with a very special situation. Okay, it happens when our common ratio, you might realise this, is a fraction. Okay, and it's a fraction between 1 and minus 1. Okay, if you have that condition where r is a fractional, then each term that you multiply by that common ratio is going to be getting a smaller and smaller and smaller until it gets infinitely small. They do this a posh way in the book. they do the modulus of r is less than 1, so even if it's minus a half, the positive value of that is a half, which is less than 1. Okay, so that's a better way, a nicer, posher way of writing it, but you know, for the purposes of this lesson, just think of it as a fraction between 1 and minus 1. I mean, you could have a common ratio of 0, can't you? That's between 1 and minus 1. And the sum to infinity would just be the first term, because everything after that is just becomes 0, doesn't it? Okay. Okay, so let's have a look at that. We just need, you do need to be able to prove the formula for that, and it's a slight adjustment to this, but you just need to know how to phrase it. Again, it's something that you learned just the night before to remind yourself of the night before, so you don't have to store it in your brains if you can't remember this. Okay, just in case you have to regurgitate it on the exam paper. And what we say, that is, we just say that when r is a fraction between 1 and minus 1, then as n gets infinitely large, so as the number of terms get infinitely large, you've got this bit here, haven't you, in the formula, r to the n. So r to the n becomes 0, doesn't it? Because if you think of a fraction, you know, to the power of 2, it becomes, is a half times a half is a quarter. To the power of 3, a half times a half times a half is an eighth. It's getting smaller and smaller. And when we do that infinite number of times to a fraction, to a number less than 1 or greater than minus 1, an infinite number of times is going to get infinitely small. You see this word limits, as n limits to infinity, it means reaches the limit of infinity, r to n limits to 0. Okay, so this happens only when r is between 1 and minus 1 in a convergent series. And when it limits to 0, then let's put that into here. We can then say that s of n is equal to a to 1 minus. Now, if we change n to infinity, okay, so the sum to infinity when r is between 1 and minus 1, we would have here r to the n would be 0, become 0. So we've got 1 minus r on the bottom. Okay, and 1 minus 0 is 1, so the sum to infinity is equal to a over 1 minus r, and that's your proof. You only have to say that, know it's in this condition, state it's in this condition, know that little bit, and then just 2 steps and you're there. Okay, so that's a special case, and it works for these what mathematicians call convergent series. Okay, so let's put that in. For the exercise, it's from exercise 3e. I'm just going to do 3e for you. 3e, well, I'm not going to do all the questions. I'm just going to do question 1 and question 10, the first and the last. Okay, so let's put our special case, sum to infinity is equal to a over 1 minus r. Okay, so that's the formula, that's the special case, and that is there's a condition, isn't there, when that, or r is between 1 and minus 1. Okay, so question 1 in the textbook, this is for exercise 3e, it says there's parts A to H, but we're only going to do the first one. It starts you off with a sequence and it asks a couple of questions, and the sequence, the first one is this one here. These are the terms of this sequence, and you can see what's happening here. And it asks you to state whether this is the series that it's given you is convergent or not. And if it is, find the sum to infinity. Okay, it's just say state with a reason. Well, this here you can see, how do we get from there to there? Well, a way of finding the common ratio, if it's not obvious, is you divide a term by the term before, and you can see that 0.1 divided by 1 is 0.1. So what we're doing is we're timesing by 0.1 each time. Okay, so this will create a convergent series. Okay, because why? It satisfies the condition that r is between 1 and minus 1, this condition here, written another way. Okay, so it's going to be convergent. You can see that these terms here are going to get infinitely small, so when you add them all together, it's going to be finite, not infinite. Okay, I prefer to use fractions, not decimals. Nicer for putting into the formula. So that, of course, is times by a tenth. All right, and if we do the sum to infinity, okay, the sum to infinity here is equal to a, the first term, which is 1 divided by 1 minus a tenth. Okay, so that's 1 divided by 9/10. And this is why I like fractions, because here, divide by 9/10, invert and multiply, gives you 10 over 9. And this here, if you added all those up, you know, or used 0.1, you've got to do an answer of 1 and a ninth in decimal form. It's not, you know, it's that 1.1111 recurring, isn't it? So it's nicer to have it written like this in fractional form. It's exact. Okay? So 1a, it's convergent because the common ratio satisfies this condition. So it will have a finite sum, and that finite sum will be, sum to infinity, will be 10/9 if we add an infinite number of terms together. Okay, so that's the first one, or 1a anyway. And then the last one, they always make the hardest question last. And so this is question 10 in the sequence. So I'll just do this one and then you can fill in the gaps. And it says the first term of a geometric sequence is 30. The sum to infinity of that sequence is 240. And you've got to do parts A, B, C and D. A, it says show that R is 7/8. Got to show that. B, 3 significant figures, the difference between the 4th and 5th terms. C, what is he saying? Calculate the sum of the first 4 terms. So I'm going to do S, sum of 4 terms. Sum of 4 terms to 3 significant figures. And D's an interesting one here. It says the sum of n terms is greater than 180. Okay, find smallest value of n. Okay, so let's do that then. The first one, so we'll do A over here. The sum to infinity is 240, so let's just put those figures into here. 240 is equal to A, which is 30 over 1 minus R. Don't put the 7/8 in to show that it works. Okay, just put it in and work it out. Move that up, move that down. So we've got 1 minus R is equal to 30 over 240, swapping those two round. And this cancels down here, doesn't it? You can see 3/24 is an eighth. So we've got 1 minus R is equal to an eighth. And so R must be 7/8, rearranging that. We've got that, first one. The difference between the 4th and the 5th terms, you've got to go back to the, work out the 4th term and the 5th term, okay? So that is going to be, remember the 4th term, when n is 4, the nth term is that AR to the n minus 1, that's the nth term, okay? AR to the n minus 1. So the 4th term and the 5th term, so I'm going to put the 4th term in first. So this is going to be A is 30, common ratio times 7/8 to the 4th term, 4 take away 1 is 3, minus 30 times 7/8. The 5th term, 5 take away 1 is 4. And you see the term's getting smaller, so this term is going to be smaller than that one, so it's best to do it that way around. Okay? And we'll just put those into our calculator, switch it on first though. So 30 times 7/8. 7/8 to the power of 3. What is that button? To the power, oops, is that to the power of 3? Does that work? Let's delete that. I'm just nervous. 7/8 to the power of 3 minus 30 times 7/8. I hope I'm doing this right, by the way, guys. Common ratio, yeah, it is. 8. I don't have to work these calculators, as you probably guess. Close my brackets. The power of 4. You're probably despairing watching this. Is equal to, and it does say 3 significant figures in the question, so if you don't do that on the exam, you will lose a mark, so it's 2.51. Okay. The sum of 4 terms. Just because this is a convergent series doesn't mean we can't use this formula, and we need to use this formula to find the sum of 4 terms. The sum of 4 terms is equal to A, 30, minus 1 minus, now 7/8. This time we use the full n, which is 4, over 1 minus 7/8. 1 minus 7/8 is 1/8, isn't it? So I'm going to go straight for that. Invert and multiply there, so I'm going to go, the sum of 4 terms is 30 times 4 is 240, nice little trick. 1 minus 7/8 to the power of 4. Okay, okay, so if I work that out, I've got 240 times, in brackets, sorry that was just someone wanted me, minus, I think I have to put this in, you might disagree, 8, close brackets, to the power of 4, and that gives me that, okay. So the sum of 4 terms is equal to, I get 99.3 to 3 significant figures, if I've stuck it in right. I hope I have. Okay. And yeah, it looks pretty good. Okay. So that's the sum of 4 terms, and this one, I like this one. Okay. This is where we're going to use a little bit of logs for D. And I don't use that greater than sign, I just put equal. So when does the sum is equal to 180? Okay. Now I know it's not going to give us a whole number, but I just like doing it that way. So what value of n in here gives us 180? A sum of that's 180. So this is, I'm going to go 30 here, 1 minus 7/8 to the power of n, all over 1 minus an eighth again, and 1 minus 7/8 again, so it's an eighth on the bottom. So therefore I get 180 is equal to 240, switching that round, 1 minus 7/8 to the power of n. So I've got that. So when I divide 180 by 240, I've now got 180 over 240 is equal to 1 minus 7/8 to the power of n. I've got that, haven't I? This obviously cancels down. 6 goes into both of these, so this can cancel down to 3/4. Okay. And if I take it over that way and that over that way, 1 take away 3/4 is 1/4, and I've got to be careful here because I don't want to run out of space. I'm now down to 7/8 all to the power of n is equal to 1/4. Okay, does that make sense to you? Okay, now then, I'm running out of space, so I'm going to move, I'm going to go back up here. I hope you're okay me rubbing this out here, and I know I'm going to work backwards. This is where we use logs, so the log of this side is equal to the log of that side, and I'm going to go the ln of 7/8 to the power of n is equal to the ln of 1/4. That's why I love logs, they're useful, aren't they? And take that down, so we've got n over n times the ln of sort of 7/8, okay, is equal to ln of 1/4. Ln of 1/4 actually is a negative value. Any fraction is or less than 1, but this is negative, so when we divide one by the other we get a positive number. So you might not realise that sort of doing it, but this is a negative divided by a negative. So we're just dividing both sides by ln of 7/8. So I can just stick that. You can use just your log button, but I always use ln. So now I'm going ln of 1/4 rubbish at this, aren't I? Divided by ln of 7/8. 7. You're despairing with me, I know you are, I can sense it. Okay, and that gives me 10.38, blah, 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 you can sort of see it. So the 10.38th term gives us 180. And the question actually says calculate the smallest possible value of n. So you can't have the 10.38th term, you can have the 10th term, or you can have the 11th term. Okay, so the 10th term would obviously, if we put n is 10 into that, it would give us a number, a sum that is slightly less than 180, and the 11th term would be the first one that is actually where it's bigger than 180. Okay, so it's the 11th, when n is 11, it's the 11th term. Okay, so you just think about it logically at the end. Now obviously there's a queue of people outside my office door waiting to speak to me about trivial things. Okay, so I'm going to stop there. And that is the sum to infinity. Okay, thank you. Bye bye.